Hi everyone. So in this video, I'm going to be going through the study guide for the Unit 7 quiz coming up. So this is one with 11 questions. You should have your ions reference sheet, you should have your solubility table, and you should have a periodic table available. So remember, we're dealing with 6 different types of reactions. So single replacement, and for that you're looking for one element by itself and one compound, meaning 2 elements. So it's like A plus BC. There could be double replacement, which is 2 different compounds that are going to switch partners, so AB plus CD. Synthesis, which is 2 separate reactants coming together to form one product. Decomposition, which is the opposite, one reactant splitting up to become 2 or more products. Neutralization or acid-base neutralization, that's when you have an acid, which starts with H, reacting with a base, which ends in OH. They come together. They act like a double replacement. You get the hydrogen from the acid to bond with hydroxide from the base, you get water, and then the other 2 ions form a salt. So basically, acid plus base yields salt plus water. And remember, in chemistry, salt can be any ionic compound. And finally, combustion. Combustion, we take some kind of hydrocarbon fuel, so some CH combination, react with oxygen to form carbon dioxide and water. All right, so what we're doing in this is we are completing these reactions. We refer to this as predicting products. So I'm telling you the 2 reactants here, and it's your job to predict the products, write out the full balanced equation, and identify the type of reaction. So a couple things to keep in mind from the instructions. Anytime the state is given or indicated, you include a state symbol, either solid, gas, liquid, or aqueous. Anytime you have a double replacement reaction, you should note whether it goes through or not. And for that, we know it will go through if we have 1 aqueous and 1 solid product. It won't go through if you have 2 aqueous products. And if it doesn't go through, you got to indicate that with no reaction. Okay, let's start going through it. So solutions of hydroiodic acid and strontium hydroxide. So right off the bat, I see 2 key words here. I see an acid and I see hydroxide. So I know this is going to be an acid-base neutralization. Acid-base neutralization. So what I'm looking for are salt and water as the products. All right, hydroiodic acid. Now we didn't do naming acids, so I'll give you the phrase here, hydrogen iodide. So hydrogen is going to be H with a plus charge, iodine is I with a minus charge. All right, so it's going to be HI, and since I tell you solutions of, that tells you that this is a solution, which means it's aqueous. All right, so HI aqueous. And strontium hydroxide. So strontium is Sr with a 2+ charge. Hydroxide is OH with a minus charge. It's going to be a 1 strontium 2 hydroxides, crisscross those charges there. And since we have 2 of those hydroxides, you need parentheses. So plus Sr OH parentheses 2. And again, solutions of, so aqueous. All right, let me just clear some space. So neutralization reactions, they act as if they're double replacements. Technically, they are a type of double replacement. So the front ion here is going to bond with the back ion here, and vice versa. So H bonds with OH gives us H2O. The strontium bonds with the iodide. And I had the ions before, but strontium being 2+, iodine being 1- gives us SrI2, strontium iodide. And now we just need to balance it. Okay, so the trick we can use for these neutralizations is to temporarily refer to the water as HOH. And now I have HI, like H ions, I ions, Sr ions, and hydroxide ions. Same thing on both sides. All right, well, let's see what needs balancing. I see 2 iodines here and 1 here, so I'm going to put a 2 there. That gives me 2 of these front hydrogen ions, 1 front hydrogen ion, 2 hydroxides, 2 hydroxides, 1 strontium, 1 strontium. So we're good, and now I'm just going to change this back to water. Number 2, a piece of aluminum. So we're just going to write aluminum. And there's only one question we ask. Is aluminum, I would call it a Brinkelhoff, or is it a diatomic? And the answer is no. The diatomic elements are HNOFClBr, not aluminum. So I just write Al. I'm not going to write Al3 plus. I'm not going to write Al3. I'm just going to write Al. Now, in terms of states, we said that if the state is given or implied, put the symbol. And when I say a piece of aluminum, I think we all know I mean a solid piece. You know, if it were liquid or gas, I wouldn't call it a piece of. All right, it's dropped into a solution of silver sulfate. So silver is Ag, which has a charge of plus. Sulfate is SO4, which has a charge of 2 minus. You're going to need 2 silvers and 1 sulfate. So Ag2SO4. No parentheses around the sulfate because there's only one of them. And I tell you it's a solution of, so that's aqueous. Okay, so what type of reaction are we looking at here? Well, I have aluminum by itself, and then I have a compound. This is going to be a single replacement reaction. Just write SR1. I know that because I have one lone element and one compound. So in single replacement reactions, generally a metal will replace another metal, or a halogen will replace another halogen, or you'll end up with a metal replacing hydrogen if it's some kind of acid, like we had in the lab. Several stations we had a metal replace the H in an acid, which produced hydrogen gas. In this case, aluminum is going to replace the silver and bond with sulfate. So one of our products is going to be aluminum bonded to sulfate. Now what you can't do is blindly grab the Al and stick it next to the SO4 and say AlSO4, because AlSO4 does not exist. It cannot exist in a 1-to-1 ratio. Well, what is aluminum sulfate? So aluminum has a charge of Al3 plus. Sulfate has a charge of SO4 2 minus. So aluminum sulfate is going to be Al2 parentheses SO4 close parentheses 3. My other product is silver. Is silver a diatomic? Is it a Brinkelhoff? No, it is not. So we just write Ag. And that's it. You know, you can assume that's going to be a solid as well, but I'm not going to require it because we didn't explicitly state that. Yeah, so that's our equation. And just please note, even though we have Ag2 right here, we are not going to put Ag2 over here. We'll fix that problem later when we balance it. But Ag it never exists as Ag2. It's not a diatomic. All right, now we just need to balance. So let's see. I see 3 sulfates and 1 sulfate, so I'm going to put a 3 there. That's 6 silvers, 2 aluminums, and I think we're good. Number 3, ethane, which is dicarbon hexahydride combusts. Now you don't need to know ethane, that's an organic chemistry term, but you do need to know this. So dicarbon hexahydride, this is going to be covalent, so we just literally take the dicarbon and write C2, hexahydride and write H6. You don't simplify this down, you don't crisscross charges, there are no charges. This is covalent, not ionic. So anytime you see these Greek prefixes here, breathe a sigh of relief because you don't even have to think about the periodic table or crossing charges or anything. Just write what's given. Combusts. You got to just know what combustion is. Combustion is plus O2 gas yields CO2 plus H2O. And now we just balance. So we've done plenty of these before. H, then C, then O. So I have H6 and H2, so I need a 3 here. Before I write a 3, I'm going to think, is that okay? And I hope you're shaking your head no. It's not okay because that'll give me an odd number of votes. So when in doubt, double it. So instead of 1 and 3, I'm going to go 2 and 6. That balances my H's out, and it keeps me even for O's. All right, now carbons, 2 times 2 is 4, so I'll put a 4 here. And now I just count my O's. 4 times 2 is 8, 6 times 1 is 6, 8 and 6 is 14, 7. Number 4, solutions of, I know I'm going to have aqueous in the front, solutions of calcium acetate and ammonium phosphate. I know this is going to be a double replacement reaction because I have AB plus CD, DRR for double replacement reaction. Double replacement reactions are like fundamentals checks. It's testing, can you successfully write formulas? Calcium acetate, calcium is Ca with a 2 plus, acetate is C2H3O2 with a minus. Ammonium, NH4 plus. Phosphate, PO4 3 minus. All right, my first compound is calcium acetate. Notice the 2 and the 1. We're going to have Ca parentheses C2H3O2 2. Because I tell you solutions of, that's aqueous. My other compound is ammonium phosphate, plus 1 and 3 minus. Okay, notice it's not 4 plus for the ammonium. It's NH4 with a charge of plus. So the 3 and the 1 swap. I end up getting parentheses NH4 close parentheses 3 PO4. Notice parentheses around the ammoniums because I have 3 of them. No parentheses around the phosphate because I have only 1 of them. Again, solutions of means aqueous. Okay. So what's going to happen here? Well, they're going to swap partners. The calcium, which is positive, is now going to switch. Instead of being bonded to the acetate, it's now going to bond with the phosphate. So I have calcium 2 plus, phosphate 3 minus, crisscross the 3 and the 2. We end up with Ca3 parentheses PO4 close parentheses 2. My other product is acetate bonding with ammonium. Positive always comes first, so it's going to be ammonium, then acetate. Notice the -1 + 1, 1-to-1 ratio. We simply write it as, and it's going to be tough to squeeze in here, NH4 C2H3O2. Okay. Let's see if we need to, let's see if this one's going to successfully occur, and if so, we'll finish it out. The way we do that, because for double replacements, you're going to need to figure out the products and then check them on the sheet here. So calcium phosphate, I check calcium phosphate, I see a solid. I'm feeling pretty good about this reaction taking place. Ideally, this S would go right after the 2, but I'm out of room. Ammonium acetate. Now, if you look at this long enough, you'll recognize that all ammoniums are always aqueous, and all acetates are always aqueous. I know that's aqueous as well. And again, that aqueous should go to the right of that last 2, but I'm out of room. So I have solid and aqueous. So yes, this reaction occurs. Okay, and now I'm going to balance it. And if it asks for a sketch, we could do that, but we don't need to. There's some sketches up here. All right, balancing. Let's see. I tend to start with my biggest term, which is the one with the largest sum of the subscripts. So I'm seeing this one here, the third term, a 3 and a 2. Let me start here. So 3 calciums, and I go back here, 1 calcium, 3. That gives me 6 acetates. I look over on the far right side. How many acetates do I have in this 4th term? Just 1. I have 1 ammonium bonded to 1 acetate. So I need 6, so I'll put a 6 there. That gives me 6 ammoniums. I look over here, I have 3, so I'll put a 2 there. 2 phosphate, 2 phosphate. Here we go. Number 5, a sample of barium nitride breaks down over time into its 2 elements. Barium nitride, Ba, 2 plus, nitride, careful, not to be confused with nitrate or nitrite. Those are both polyatomic ions. But nitride is just regular old N with a charge of 3 minus. So barium nitride is Ba3 and 2. Breaks down over time into its 2 elements. This is going to be decomposition. We have 1 reactant yielding more than 1 product. Anytime you have just one thing by itself on the left, it's going to be decomposition. All right, its 2 elements are barium and nitrogen. Notice I'm not calling it nitride if it's just regular old nitrogen. Like when N is in its elemental form, we call it nitrogen. When it bonds to other things, we call it nitride. So the question we ask is barium a diatomic? Is it a Brinkelhoff? No, it's not. So we just write Ba plus nitrogen. Is nitrogen a Brinkelhoff? Yes, it is. So we say N2. All right, now we just need to balance. So N2 is already balanced, 3 bariums, 3 bariums, just like that. And type of reaction, decom. Decomposition. All right, number 6, a solution of sodium iodide is reacted with chlorine gas. Is reacted with sounds weird, maybe reacts with. All right, so sodium iodide, Na with a plus charge, I with a minus charge, NaI. And by now we know solution of means aqueous, reacts with chlorine gas. So we have chlorine by itself, the gas just tells you the state. Is chlorine a Brinkelhoff? Yes, it is. So we say plus Cl2. All right, let's look for what's going to happen here. So the type of reaction, we have a compound and a lone element. So the lone element, now you could be saying that's not a lone element. There's 2 chlorines. They're not alone. Well, it's still considered a lone element because it's only one type of element there. Even though it's diatomic, it's not bonded to any, it's not a compound. So this chlorine is like, I would say, the bully at the school dance that's going to swap places with one of these. So the question is, which of these 2, the Na or the I, is the chlorine going to want to replace? And the answer is the iodine, because halogens will replace other halogens. Makes sense, because chlorine forms a negative charge, so it's going to replace the negative and bond with the positive. Okay. But what you can't do is blindly stick the Na and the Cl2 together and say NaCl2. I mean, you all knew this walking into chemistry on day 1. That sodium chloride is NaCl, not NaCl2. So we're going to form sodium chloride, which is NaCl, plus 1 minus 1. The iodine got booted out. It's kicked. It's on its own. So we just write plus iodine. Now in the formula, you're going to put that as I2 because it's a diatomic. It's a Brinkelhoff. All right, now we balance this one out. Just give it 2 there. And then 2 there. And for type of reaction, single replacement reaction. Number 7, a piece of cesium burns in air. Cesium is Cs. Is cesium a diatomic? No, it is not. So we just write Cs. And a piece of it is going to mean solid. Cs, solid. Burns in air means plus O2 gas. All right, so what type of reaction is this going to be? Well, we just have 2 lone elements here. They're going to come together in a synthesis reaction, not combustion. A lot of people think anytime anything burns, it's combustion. Nope. Combustion requires a hydrocarbon fuel producing carbon dioxide and water. For this one, it's just going to be synthesis. So cesium and oxygen come together to form cesium oxide. But again, we can't just blindly smush together and call it CsO2. Can't do that. You got to think. When cesium bonds with oxygen, what do we get? Well, cesium is Cs plus. Oxide, oxygen is O2 minus. You crisscross it, our product ends up being CS2O. And now we balance. So let's see. 2 oxygen, 4 cesium, 4 cesium. And our reaction type is synthesis. Number 8, 2 solutions are mixed. I already know right off the bat it's going to be double replacement. Actually, I should be careful because if it said 2 solutions are mixed and one of them is an acid and one is a base, then it's going to be a neutralization. But for this one, I don't see any hydrogen or hydroxide, so I know it's going to be a double replacement reaction. All right, 2 solutions are mixed. So as I said before, double replacements are like checking on how well you can write formulas. So magnesium is Mg2+, bromine is Br-, aluminum is Al3+, acetate is C2H3O2-. Okay, so magnesium bromide, crisscross that, we get MgBr2. Solutions, aqueous. Aluminum acetate, aluminum 3+, acetate 1-, crisscross Al parentheses C2H3O2-3, aqueous, because it's solutions of. All right, so these are like 4 friends at the school dance. Magnesium's dancing with bromine, aluminum's dancing with acetate. Next song, let's switch partners. Magnesium's now going to bond with the other negative, acetate. Aluminum's going to bond with bromine. So we're going to get magnesium acetate, which is going to be a 2-to-1 ratio here. So Mg C2H3O2 2 plus, hopefully you don't run out of room here, I should be fine. Aluminum bromide is going to be AlBr3. Okay. Now for double replacements, we need to know the states at the end here. So the states are going to be, well, magnesium acetate. In fact, I remember that all acetates are always aqueous, so I don't even need to check. Aluminum bromide, also aqueous. So for this one, no reaction. Aqueous means no reaction. And why? Because we really started with a beaker of not magnesium bromide. We started with a magnesium bromide solution, meaning magnesium ions and bromide ions randomly floating around in water. We added it to a beaker of aluminum ions and acetate ions randomly floating around in water. What do we end up with? Magnesium and acetate ions randomly floating around in water, aluminum and bromide ions randomly floating around in water. Notice how nothing really happened, so no reaction. And we don't even need to balance it because there is no reaction. I mean, if you did want to balance it, you could. You're not wrong to balance it. It's just no reaction took place. No need to balance. And for reaction type, as we said before, it would be a double replacement, but no reaction actually took place. All right, number 9. Oh, this is a sketch we have to do. So I guess I didn't totally clarify. Solutions of zinc acetate and ammonium oxide are mixed, presumably. Okay, so zinc acetate is Zn2+, that's zinc. Acetate is C2H3O2-. Let me write the other ions. So ammonium is NH4+, oxide is O2-. So my zinc acetate is going to be Zn C2H3O2-2, and since I say solutions of, that's aqueous. Ammonium oxide, 2 ammonium, so NH4 in parentheses, 2O, and that's a solution as well, so aqueous. All right, I'm going to go a little quicker through this. The zinc bonds with the oxide gives us ZnO. The ammonium bonds with the acetate gives us NH4C2H3O2. All right, before we balance, let's see if we even have to balance. Let's see if this will go through. So I know that ammonium and acetate are always aqueous, so I'm going to fill that in. Zinc oxide. But this is zinc 2. It doesn't need to say zinc 2. It could just say zinc because zinc always goes with 2+. Anyway, zinc oxide solid. Here's our precipitate. So yes, we have a reaction. Let me just shift this up a little bit. Just make sure the picture doesn't get cut off. All right, so for sketching this, we're going to have beaker number 1 plus beaker number 2 yields beaker number 3. Our aqueous terms get split up into ions and interact with water. Our solid terms settle to the bottom and stay together. All right, we have zinc acetate. So I'm going to have a zinc ion, Zn2+. I'm going to have an acetate ion, C2H3O2-. I'm going to have waters that point with the oxygen facing the positive ion and the 2 hydrogens facing the negative ion. The 2 hydrogens are positively charged and the oxygen is negatively charged. Second beaker, I have ammonium and oxide ions. So NH4+, O2-, 2-, and my waters are going to face towards the ammonium and away from the oxide. Final beaker, I have ZnO solid, which means my ZnO is at the bottom, and I like to draw the line to show that it like literally settles out. Ammonium acetate is aqueous, so I put my ammonium NH4+, and my acetate C2H3O2-. I'm going to show waters interacting with these. And that's it. So I have a precipitate in the ZnO, and another vocab term, the ammonium and the acetate ions are spectator ions, because notice, They didn't do anything. They just kind of watched. The ammonium started out floating in water next to the oxide. The acetate started out floating in water next to the zinc. The zinc and the oxygen actually did something. They found each other and bonded and settled at the bottom as a precipitate. What did these do? Nothing. They're still floating around in water. So spectator ions. Number 10. Strontium chlorate solution added to aluminum chloride solution. All right. Strontium is Sr2 plus. Chlorate, this is one I rarely use. I got to think. These are 4 that are similar. Chlorate would be ClO3 with a minus charge. Let me confirm that. Chlorate, yep. ClO3 with a minus charge. Aluminum is Al3 plus. Chloride, Cl minus. All right, so my formula, my equation is Sr 2 and 1, so it's ClO3 2. That's strontium chlorate. Aqueous because it says solution. Plus aluminum. Wait, did I balance the last one? Oops. Forgot to balance the last one. I don't know why that came to me just now. So zinc acetate looks good. All right, it looks like the only thing I need to add is a 2 in front of that ammonium acetate. Number 10. So that's my strontium chlorate. My aluminum chloride is going to be AlCl3, and that's also aqueous. So the strontium bonds with the chloride, giving us SrCl2. The aluminum bonds with the chlorate, giving us AlClO3 in parentheses 3. Ooh, I'm not used to that chlorate. So ClO3 is chlorate with a charge of minus, so it's 3 up there. Okay, let's check our states. So strontium chloride, aqueous. Aluminum chlorate, aqueous. So we have aqueous, aqueous. We need to clearly write no reaction. There's no reaction. There's no need to balance it since there's no reaction. But we are still asked to sketch this one, so let's do that. Beaker number 1 plus beaker number 2, beaker number 3. Strontium is Sr with a 2 plus. Chlorate is ClO3 with a minus. Let me just sketch all my ions. Aluminum chloride, so I have aluminum ion, Al3 plus, chloride ion, Cl minus. Please note, chlorine is a Brinkelhoff, yes, but that's not when it's in its ionic form. When it's an ion, it's an individual chloride ion. Here I have strontium chloride aqueous, so Sr2 plus and Cl minus. I also have aluminum chlorate aqueous, so Al3 plus. Oh, that's not correct. Al with a charge of 3 plus. And chlorate is ClO3 with a charge of minus. And now we just need to show water is interacting with these. Okay, yep, I'm pointing in the right direction. And then down here, pointing towards the positives and away from the negatives as best we can. Something like that. All right, and now you could again see why there's no reaction. Because look, we started out with strontium and chlorate ions randomly floating in water, aluminum and chloride ions randomly floating in water. Look what we have. Strontium, aluminum, chloride, and chlorate ions randomly floating around in water. We took 2 batches of ionic soup, mixed them in, and got 1 batch of ionic soup. We didn't really make anything. No reaction. Last one. Ammonium phosphate, NH4 plus. That's ammonium. Phosphate is PO4 3 minus. Magnesium, Mg2 plus. Iodide, I minus. So ammonium phosphate is going to be parentheses NH4 close parentheses 3 PO4. And because it's a solution, we say aqueous plus magnesium iodide, MgI2, aqueous. Okay, so the ammonium bonds with the iodide, NH4 plus, I minus gives us NH4I. No parentheses because there's only one ammonium. Plus magnesium bonds with phosphate. Mg2 plus, PO4 minus gives us Mg3, parentheses PO4, close parentheses 2. We check our pink solubility table. I know that all ammoniums are always aqueous, except for the ammonium oxide, which does not exist. So we're going to call that aqueous. Magnesium phosphate, solid. Solid. So yes, this does react, which means we have to balance it. Let's see, there's my biggest term at the end. So I'm going to go 3 magnesium, 3 magnesium. That's 6 iodine, 6 iodine. That's 6 ammoniums, 6 ammoniums, 2 phosphate, 2 phosphate. Right, now we just have to sketch this. Let me shift this up a little bit. See if I can grab all that at once. All right, beaker number 1 plus beaker number 2, beaker number 3. Ammonium is NH4 with a plus charge. Phosphate is PO4 with a 3 minus charge. Magnesium is Mg2 plus. Iodine is I minus. Over in this products beaker, I have my solid Mg3 parentheses PO4 close parentheses 2 at the bottom, settled out. And that's written together. It's not written as magnesium and phosphate. It's together. My ammonium iodide is aqueous, so we write NH4 plus, I minus. Now the last thing we do is add some waters to interact with these ions. There we go. Okay, that's it.